All right, let's just jump right into this explainer and tackle the exact problem that literally makes engineering students break out in a cold sweat. You know the feeling, right? You're sitting there in a lecture hall, staring up at a whiteboard completely covered in Greek letters and vector calculus, and you're just wondering how on earth a simple piece of copper wire turned into an absolute mathematical nightmare. Well, today, we're going to fix that. And hey, don't just take my word for it. Dr. Matthew Sadiku's widely used textbook flat out admits, quote, Electromagnetic theory is generally regarded by students as one of the most difficult courses in physics or the electrical engineering curriculum, end quote. So if you've been dreading this subject, you're definitely not alone, but here is my promise to you. By the end of this explainer, you're going to know exactly how to conquer conductor boundary problems and calculate internal fields with total confidence. So the whole foundational difference in all of electromagnetic material theory really just comes down to one simple question. How many free electrons are ready to move? Conductors, your metals like copper and aluminum, they are the absolute VIPs of current flow. They've got a massive abundance of free electrons. Insulators, or dielectrics, like glass or rubber, they have almost none. It's kind of like picturing conductors as this wide-open multi-lane superhighway, whereas insulators are just a highway completely jammed with parked cars. Now, focusing on that wide-open highway of conductors, we hit a super critical concept. When a perfect conductor is isolated in an electric field, it becomes what we call an equipotential body. And this is a massive, highly counterintuitive rule you really need to lock down. Under static conditions, the electric field inside a perfect isolated conductor is exactly zero. The voltage potential is exactly the same everywhere across the material. But why does that happen? How does a powerful external field just magically vanish inside the metal? Okay, let's use a visual analogy. I want you to picture a giant shield wall. Think of the free electrons inside the metal as these highly trained, incredibly efficient bouncers at an exclusive club. The exact moment an external electric field tries to force its way in, these electron bouncers instantly rush to the outer edge. They physically rearrange themselves to form an absolutely impenetrable wall of charge, creating their own induced field that perfectly cancels out the external one. They take the hit on the surface, right? So the VIP interior stays completely field-free. And that beautifully illustrates the strict mathematical rules right at the conductor's boundary. Because of our electron shield wall, three specific things happen at the interface between the conductor and free space. First, the tangential electric field is absolutely zero. Literally nothing flows sideways along the surface. Second, the normal electric flux density exactly equals the surface charge density. And third, this is the big visual takeaway here. Electric flux leaves the conductor surface at a perfect 90-degree normal angle. Every single field line points straight out, almost like spears bristling from our shield wall. All right, now let's build our mathematical weapons. We've got to link these microscopic, totally invisible fields to the macroscopic resistance you'd actually measure with a multimeter. Your two core formulas are these. First up, the point form of Ohm's law, where current density, J, equals the material's conductivity, sigma, multiplied by the electric field, E. Second, the total resistance, R, equals the length of the conductor divided by its conductivity times its cross-sectional area. So let's actually put these formulas to the test with a classic real-world exam problem straight from the text. Imagine we've got a conducting wire. It has a radius of 2 millimeters and a length of 100 meters. We apply a DC voltage of 9 volts right across the ends, and that gives us a current of 0.3 amps. Our mission? We need to find the uniform electric field inside the wire and calculate its exact conductivity. Let's break this down step by step. The absolutely crucial first step is to just start simple. We find the uniform electric field by dividing our 9 volts by the 100-meter length of the wire. Since the field is perfectly uniform here, E just equals V over L. So plugging in those values, 9 divided by 100 gives us exactly 0.09 volts per meter. That right there is the actual driving force that's pushing our electrons down the length of the wire. Okay, next up, we need two more pieces of the puzzle before we can hunt down the conductivity. First, standard macroscopic Ohm's law easily gives us resistance. R equals V divided by I. So 9 volts divided by 0.3 amps is exactly 30 ohms. Easy enough, right? Second, we use basic geometry to find the cross-sectional area. area, S, equals pi times radius squared. And guys, here's a massive pro tip. Always remember to convert your millimeters to meters. Pi times 0.002 squared gives us this really tiny cross-sectional area of 0.0000126 square meters. All right, now we isolate conductivity to get our final answer. By just rearranging our resistance formula, conductivity, or sigma, equals the length divided by the resistance times the cross-sectional area. We put our 100-meter length on top. On the bottom, we multiply our newly found 30 ohms of resistance by our tiny area of 0.0000126. Crunching that denominator first yields 0.0003768. Finally, you just divide 100 by that decimal. And boom! The math reveals our conducting wire has a conductivity of roughly 265,258 Siemens per meter. If you were to check standard engineering tables, you'd see this is a very solid conductive material, even if it's maybe not quite pure copper. But seriously, think about how incredible that is. We took a macroscopic, real-world readings, literally just voltage and current, and used them to perfectly derive the microscopic electrical properties of the metal. That's pretty wild. But wait a second. Earlier, I told you the internal E field is always zero, right? Yet in the math problem we literally just did, we calculated an internal field of 0.09 volts per meter. What gives? Well, this brings us to the ultimate trap. This is the gotcha that trips up almost every engineering student on exam day. We're looking at case B, a conductor maintained at a potential. The source text clears this paradox up beautifully. It states, quote, "There is no static equilibrium, since the conductor is not isolated but is wired to a source of electromotive force which compels the free charges to move." End quote. Think about it. If a conductor is actually wired up to a battery, just like in our 100-meter wire example, the rule of the isolated shield wall is totally broken. The battery is acting like a massive pump constantly pushing charges, so there is zero static equilibrium. Therefore, an electric field absolutely must exist inside the conductor to sustain that current against the material's internal resistance. Okay, let's lock this into your brain before we wrap up. To survive your exam, never forget these 3 rapid-fire rules about conductive materials. Rule 1. Isolated conductors act as perfect shield walls where the internal E field is always zero. Rule 2. At the boundary of that shield wall, electric fields are always completely perpendicular to the surface. Rule 3. Wired conductors break the isolated rule entirely, actively harboring internal fields to sustain continuous current flow. Honestly, if you can just master that difference between an isolated shield wall and a wired conductor, you're going to be light years ahead of the curve. Hit subscribe for more EMC survival guides, and until next time, I really want you to ask yourself, what happens to this electron shield wall if the external field isn't static, but instead it alternates at 1 billion times per second? I'll give you a hint. The charges violently crowd the surface in a phenomenon called the skin effect, and it completely changes the game. See you in the next explainer.